Hello ladies and gentlemen, my name is Julio Martinez. Welcome to my instructional video of calculating line capacitance on a three-phase transmission line with the use of MATLAB. As we can see in the image before us, we have a three-phase transmission line tower composed of two conductors per phase. These conductors typically come in bundles 2, 3, 4, or more. Taking a look at a cross-sectional area of our transmission line, we have phase 1, 2, 3, along with the sending end conductors A, B, C, and the receiving end conductors A', B', C'. The things to note from this diagram are the distances between phase 1 and 2, phase 2 and 3. Also, the distance between phase 1 and 3. We also want to take note, in between the conductors, we want to note at the centers the distance between each one. The transmission line conductors are composed of aluminum conductors steel reinforced, or ACSR. They come a variety of 31 choices. These choices are labeled under bird names, don't know why, but that's what they use. And the things that we want to note from this table is the outer diameter of the conductor. Since we're dealing with alternate current, AC, at 60 Hz, we want to take into account the resistance of the line at the temperature of 20 Celsius, or the resistance of the line at 50 degrees Celsius. We can also note the GMR, or the geometric radius, for each stranded conductor. Now let's get into some math. Since we're dealing with a two-strand bundled conductor, first we want to take into account the geometric mean radius given by this equation, the geometric mean distance, which is composed of the distance in between the sets of conductors to that root. Here we have the capacitance of the line in neutral, as well as the reactance, which is given in phasor form. We also want to take into account the charging current. Now we move into the MATLAB portion, as I have previously written out this program. First I want to take in the inputs from the user, which consists of the voltage of the system, the length in miles of the transmission line, the number of bundles, the distance between those bundles, the number of conductors per bundle, as well as the distance separating those conductors. Also, we want to take into account the ACSR code that the user is using. Here in our constants, we have the distance between those conductors, which is the center, as you recall from the diagram, is 20 inches, transmitted into feet. We also have the distance from the first phase set of bundled conductors to the third phase set of bundle conductors, which is the total distance of the transmission line across from the previous diagram. Here we have the frequency, since we're dealing with 60 Hz, and our permittivity of free space, which is used in our capacitance. Considering that we have a varied amount of conductors, I had to compose a function which could contain all the information of the conductors. Let's take a look at that now. So here we have the function that we want to create in a separate script file, and we want to save under the function format, which consists of the function name, or the file name as well, with the input parameter and the output parameter, the geometric mean distance of a single conductor, the diameter of that conductor, and the resistance at 20 degrees Celsius, resistance at 50 degrees Celsius. What I composed was a switch case of 31 choices, which consists of the variations of a string. There the user can type in either in lowercase, uppercase, or with uppercase and lowercase to choose their ACSR conductor. Now we're using two of the outputs from the function. One is the diameter of the conductor, and the other is the resistance at 20 degrees Celsius. With the diameter of the conductor, take into account the radius, where we divide by 2, and since we're going from inches to feet, we do conversion here. Now going into our equations from our previous slide, we have our geometric mean radius, composed of the radius times the distance of the diameter between the conductors, and we have our geometric mean distance, composed of the bundle distances between the phases, phase 1 to 2, 2 to 3, and 3 to 1. And we have our capacitance to neutral, which is 2 pi times the permittivity of free space over the logarithm of the geometric mean distance over the geometric mean radius. Next we find reactant, capacitance, in phasor form, and then we have our susceptance, and here we have our charging current, which is the voltage from line to neutral. So we're taking that voltage that the user puts in, which is considered the voltage from line to line, divided by the square root of 3, and that gives us the voltage from line to neutral, which we multiply by our susceptance. It gives us our charging current. And here we also have our reactive power, which we did not mention in the equation, but it is square root of 3 times the voltage from line to line times our charging current and times the length of our transmission line, output of our program. Now, let's see how our program works. Let's say 5,000. Let's say we have 300 miles transmission line. Number of bundles, we have 3. Distance between each bundle is 20. And number of conductors per bundle is 2. Distance from status 35 feet. And let's say we're using ACSR. There we go. And that concludes our tutorial video. Hope you enjoyed. Thank you.